me know if he abandons you on the bus, because he went to go get groceries, and I was like, oh, we're not going to ride back together? Okay, well, I guess I'm on my own.
I agree with you. Yeah, you have no problem. You send me by email, right?
Yes.
Because I didn't print out.
Oh,
okay.
you did.
You did a good job, so I don't need that.
Okay.
Okay.
Thank you.
You're welcome.
They don't come up.
How about other guys?
Don't know earlier.
No any other exam, right?
Oh well, if they do come, they'll come together.
Yeah. Okay. I think let me write down. I think we almost finished this. Okay. Write down the final expression which we derived end of last class. So this total kinetic energy is, we have these terms. First is half of Li partial Ri partial T square plus another summation from 1 to n Mi j from 1 to n capital N lower n partial Ri partial Q J I partial T and plus half of inside I have 2 summation J 1 to N K 1 to N partial R I partial Q J dot partial R I partial Q Q K Q J dot Q K dot. I think we ended this one, right? Last time. Okay, you may ask why we do that. This is my goal. The goal I try to find, we introduce the Jacobi integration we call the energy function H. This defines this term, but is this just, when we say energy function does not mean it's energy, so we are going to find in which condition it's equal to energy. So we start from the kinetic energy. Now I'm going to write this way, T naught plus T1 plus T2. I separate these 3 terms into these 3 terms. So here, T naught, you can see is this one, right? I'm going to write I use M naught. So here, M naught is the term, sum of all the particle of Mi, and only depend on the I, right? That is this first term. So that is, okay. That is zeroth order in the QJ dot, right? No QJ dot, just zeroth order. Then that's why we use T naught. And T1 is the second term. Second term here is, since this is 2 summation, right? I'm taking the J outside, so that is summation J from 1 to N, Mj, QJ dot. You see here? Wait a second. Oh, sorry, not QJ dot. I think I missed one. Yeah, here, QJ dot. This one, QJ dot. So that's the QJ dot here. And then here, Mj is summation for all the particle here, half or no halves. So we have 2 terms. Mi is this term, right? Mi partial, your partial Ri, partial Qj dot, partial Ri, partial T. So that is the first order in Qj dot, right? That we correct, because those are coefficients, so we use the Mj to represent all the coefficients. When I say coefficient, it's a coefficient in terms of the QJ dot, or M naught is coefficient in QJ in terms of the QJ dot, which is 0th order. Then the third term is we give this half of, we have 2 summation, right? J from 1 to N, K from 1 to N, Mjk, Qj dot, Qk dot. So here, this Mjk is the index of 2 J and K, right? So that is this inside. This is a summation from 1 to N, half of. Okay, now half is here, so no half. Half is put here, right? That is summation and Mi partial Ri partial Qj inner product partial Ri partial Qk. So this one is a second order or project term in Qj dot. We just classify this into the whether it is a linear or 0th order or second order in the generalized velocity. So now when we write this kinetic energy in terms of this, then now let's look at the quantity. Now quantity is T minus U, right? V, right? Okay. So now T we separate into 3 terms. Okay. So then we can write this way. We also classify the Lagrange into three terms. L0 plus L1 plus L2. Okay, so L0 is only function of generalized coordinates and time. So that is 0, zeroth order in QJ dot. Then we classify all the terms which is linear in the QJ dot with L1. So that is function QJ dot, and T. This is the first. Okay, then L2. First write down here. Then we are going to discuss which L0 include which term on L1, L2, right? So that is second order. Okay. Then when we classify this, now we can discuss what is L0. So let's say if the V is only a function of generalized coordinates, then that is not the function of QJ dot, right? So the L, okay, L0 is T0 minus V, right? Since they are all the zeroth order. Then this L1 is T1, L2 is T2, right? Since only T1, T2 is either linear or second order of this the general coordinates. But if the U is we have a potential is, remember, if in case the potential is function of only of the general coordinate but also function of general velocity, in this case, then this L0 is T minus U0, T0 minus U0, because U also has several terms, right? So L1 in general is T1 minus U1. We do not know U1 which formula, but assume in general is T2 minus U2. Okay, so now we almost reached to find the condition, but we need to apply the Euler theorem. So now we are going to apply Euler theorem. This Euler theorem is that if a function f is homogeneous, homogeneous function of the degree in the variable xi. Then we have this. So sum of all the xi partial f partial xi multiply xi equal to n. Okay. So how to understand this? Let's look here. Example. Let's see how. Let's look this one first. So for L0, right? L0, since that is zeroth order in QJ dot, right? So L0 is, okay, for L0, let's just, for L0, because n equal to 0, I mean, let's consider that is, you are here, xi is in our case QJ dot. So we are going to see if the function in terms of QJ dot, which degree, right, is 0. So, okay, we have a summation of g from 1 to n partial L0 partial QJ dot is equal to n, right? And that equal to 0. That is what we apply. Because this will give us very easier way to get this sum term. So now then for L1, because n equal to 1, right? That is first order in the general coordinate. So summation j from 1 to n partial u1 partial qj dot qj dot is n which is equal to 1. Yeah, fine. Sorry, I think it is nf. So that is n L1. Wait a second. N L1, which is L1. Okay. Oh, he is not come, right? He will. Oh, okay. Move to your side. That. Okay. So L2. For L2, we know because n equal to 2, right? Second order in general velocity. So according to the Euler theorem, this summation g from 1 to n partial L2 partial qj dot should be equal to n L2, n is 2, so 2 L2. By this, now we can rewrite the h. So now, let's here, h is here, right? So I think I can. Can I use? Okay. So that
T naught to T naught equal to Tm Tm naught. That is from today's lecture. T equal to T naught plus T1 plus T2. That was we already discussed in.
Yeah, we just this is the end of last class. Yes. So now I just start from here.
Yeah.
Okay. Now we come back to see the h, right? So the h. Now we come back to h. H here is summation j from 1 to n partial L partial qj dot, right? That is why we are looking at and qj dot. This term we are going to deal with. We are going to apply this Euler theorem. So now, since L, let's first. L has L naught, L1, L2, right? So this also has three terms. So now, summation j from 1 to n partial L naught partial qj dot plus n partial L1 partial qj dot plus from 1 to n partial L2 partial qj dot minus L. So minus L, L has L naught minus L1 minus L2, right? Can I erase this part?
Yeah.
Okay. So now we're going to apply this. The first term is 0, right? That is very easy if we apply the Euler theorem and very easy to deal with this. The second term is L1, right? That is L1. The third term is 2L2. And then this one, right? So this, and then minus L0, minus L1, minus L2. So this one cancel. Therefore, we have this 2 we have 1, so there's L2 minus L0. Simply, this case, we didn't discuss in details any condition. Just introduce or separate this Lagrange in terms of the generalized velocity. Zeroth order, first order, second order. So the h is here. Okay. Now we can discuss. So now we're going to discuss if actually we need two conditions. If first partial Ri partial t equal to 0. That means, and this is the most case we have implied this implied dependent on this time, but that's not explicitly, right? So what happened you see here? This term equal to 0. So that means this term equal to 0. This term disappeared, right? Second one, the M1, this P1, this term also disappeared, right? Because it's 0. So Okay, that is, so then T equal to, T naught is only T2, right? Only conjecture that we know if this is the total kinetic energy is R dot square, but now this T2 is general velocity square, right? So that is different. Okay, so then when we have this condition. And second, the U is only function, I mean, so V is only function general coordinates. And this is also most case. So then this means L naught here. L naught here. L naught, huh? Okay, here, right? L naught is T naught minus V, but T naught is 0, so negative V. Okay, and then the L1, so now let's see L1. In this case, because you see here, this is also, okay, you know, so then if here, then L1 equal to T1 also equal to 0, right? And so we just consider, we do not, but this is not the case, so we just consider this case, this condition. Maybe just put here with the second, assume second, right? So here L1 is 0. Because T1 is 0, right? In this case T1, let me say T0, T1 is 0, T1 is 0. So we have this, so this L1, and then L2 is T2. That makes sense? Then let's see, H. H is L2 minus L0, right? L2 is T2. Minus L0 is plus V, right? T2 is T. So this is AJ. Okay, that makes sense. So now the energy function H, when it is equal to the energy of the system, physical quantity of system, when if we look this R does not depend on time explicitly, and the potential to be only the function of the general coordinates, then the equal. Okay, that is condition for the for this energy equal to energy function equal to the total energy. Now let's discuss. We have two small topics discussion. One, we introduce the energy function. Another, we want to see when the energy function equal to the total energy. So now, first, be careful is, okay, in general, you know, H does not equal to E, right? That is here. So if H is equal to constant, that means partial L, partial T equal to 0, so there's a dH dt equal to 0. It does not mean energy is conserved. Energy function conserved, but does not mean energy conserved. We need to double check, right? So that is the first issue you need to be careful. Second, okay, H depends on the choice of general coordinates. Because here, you see, if you select different, it will different, right? This term depends on general coordinates. So, because this, that means in different, like in Cartesian or in spherical coordinates, they are different. This H, that is, but L, if you remember L Lagrangian, which is physically the difference of total energy and potential energy, and energy is a function of, it's a class of total energy and potential energy, do not depend on the choice general coordinates. When I say does not mean the value, okay, maybe the value. The expression may differ, right? So for example, kinetic energy, if in the Cartesian is half m x dot square plus y dot square plus z dot square, but in the spherical is r dot square and r square, c dot something. So expression different, but the values we same. Like this is characterized physics. So let me see that. The value. Oh, right. Let's do this way. But this, both expression and value will depend. So that is different. Okay, I think that is two important things I want to point out. The other one, which I want to speak that one, I think this one I already discussed, is introduce the diffraction force, which is a Cartesian function, and we already proved, I think I did, right? That is characterize this change of this the rate of energy loss. Okay, let me just quickly go through this one. So, discuss S3. If we have this diffraction force is written in terms of Cartesian function. Right? That is, if this exists, then we know the Lagrange equation is chapter 1, if you remember. Qj dot minus partial L partial Qj and plus Qj dot, right? Equal to 0. From here, I erase here, and from here, then what is the total L, total time derivative of this one? We have, okay, partial L, partial Qj, Qj dot plus partial L, partial Qj dot, Qj double dot plus partial L, partial T. So add these two together. We also find, finally, I think, do the same thing. So now I just give you final is this. So finally we have dH, dt, okay, equal to minus partial L partial T, which is without this fraction, right? Now we add another term, and plus, okay, here, then this, and then, I think this summation, right? That is for, okay, this for each one. So we have a summation here. Then we have a summation, so that is a partial. And this one we apply this Euler theorem, that is minus partial L, partial T minus 2. That is additional term here, right? We have additional term if we have fraction. So even if the partial L partial T equal to 0, even in this case, the total time derivative of this the energy function is not equal to 0. It is equal to this. Does not keep constant because we have a fraction, so that gives us the energy rate, or we can negative sign, right? So that the energy loss per time. That is loss go to where? Go to against the fractional force, right? That is the only things I just want to repeat here, since we have discussed this in the chapter 1. So I just quickly remind you, if we discuss the energy function, we also need to understand this relation between energy function and this dissipation function. If, remember this dissipation function, right? Dissipation function. Chapter 9. Okay, so far we have covered all the topics in chapter 2 and at the combined chapter 1. So what we have? We introduce Lagrangian. The goal is try to transform from Newtonian mechanics to the analytical mechanics, since in the analytic mechanics, not only we deal with this not vector analysis, but the scalar analysis, and also we need see the advantage can extend to the other field, right? So now we're going to apply. So here we all just derive this all this theory here. Now we are going to apply. How to apply the Lagrange's equations to the system, right? We are going to apply. And one example, since we do not have time to cover all the other cases, so for this textbook, I select only the central force. Let's go to the central force problem. Okay. Since this one is very famous or very popular, if you, some of you maybe major or interested in the astronomy, or even this the commencement will also deal with the interaction between the particle like electron Coulomb force or gravitational force. Those are central force. So how to apply the Lagrange equation to deal with this type of a problem, and how to solve the equation of motion, how to understand what kind of motion it takes, right? So that is chapter 3. Okay, let's start chapter 3. So chapter 3, when we say the central force, we focus on, we have two objects or particles. And then we know the color, we know the force. If we say the central force means the force along the line between these two, right? So if this one feel the force exists from M1, that may be repulsive, let's just along line. So that if I say that is the F1, 2, that is the particle 1 exert force on 2, right? So that is, if it is attractive, the particle 2 will move to this direction. This is F1. Particle 2 exert force on particle 1, so try to attract this particle 1 to go to this direction. So here, we have, that is example, then we know the central force follow this Newton's second law, right? The inaction, action reaction. So that is obey the weak law. Remember in chapter 1, we introduced what is weak law of action reaction. Action reaction. The weak law means if the force, these two forces are same magnitude but opposite direction. Second one, if you see this force along this line between the two particles, right? So the force is also parallel. If we see this R and G, this distance along this the line between two. So that is, this is obey its strong law. Right? Remember we have also the strong law of action reaction. So in the central force problem, both satisfy. Then we only consider interaction between the particles, so there is no external force. If you say the light, whatever light or each individual, the force is 0, right? So we already analyzed the chapter 1 for many particle systems. If the total external force is 0, this total linear momentum of this n particle system equal to total the linear momentum of central mass, that is constant. It's conserved, right? That is the just use that result since we already discussed. Then also, the external torque is also 0, right? We just, this central force, and you know this central force along the line, so there's no, rotate moment arm, right? So that is 0. Then we have this total angular momentum is constant, right? So that is probably before we do this, deal with the system in details, we first need to analyze and see how much the physical information or usable information we can extract from the system before doing that. That will make our very clear what type of system or what feature of system, and when we deal with the details, apply the Lagrange equation, it makes the equation simple, right? So, okay. So that is the force analysis. Then, what we are focused, or our goal? Focus. Our focus, right? So yes. Well, what is we are interested? Okay. We are interested in the equation of motion, or the motion of this particle with under the central force, right? So there are two major. First, what is the orbit motion, right? What type of orbit? Second one is, how about the conservation? The physical quantities conserved or not during the motion, right? So these two categories, and for the orbit, we have the details. Either the closed orbit or open orbit, right? So for closed orbit, either circle or ellipse. Okay, for the open, either this orbit like a parabolic, parabola, and another is hyperbolic, hyperbola. Okay. For the closed orbit, the typical example is like Kepler problem. Kepler problem, we know that Kepler observed the sky, right? Planet, the stars. So that all the force is 1r squared. Here, I didn't give any details of force formula. Only function r, maybe r 1 over r, 1 over square, 1 over r cube. So this is the only particular case. If 1 over r square, we know this one. So that is like some phenomena like sweeping. Interesting about how about the sweeping area of constant or not. We have a Kepler's the first law, second law, and how about the period? I mean the period for the orbit, and then some of Kepler's laws. That is the issue. That's how it is. Then for this, most cases scattering. Scatter problems. And scattering that if you look at the sky, it's scattering like some of the planet is not close orbit, right? Come close to the sun and go out. Or in the experiment, if you go to this high energy, look at the particle, the like charged particle or electron, and with a very high energy, and try to close to the target and go out. Right? So those are this type of problem. Okay. Now conservation. Conservation, we are interested. How about energy, right? Energy conservation. And orbital angular momentum. Since here, the linear moment of the many particle, this is two particle center mass, will keep it constant. So that is not the more interested. We just interested how the relative motion of the particle during in this central pose. So that is the interest topic we are going to focus in this chapter. Now let's start. So we are going to figure out how to describe those systems, how to select these general coordinates. Then once we select general coordinates, we are going to apply the Lagrange equation, right? So that is step by step. So next step, okay, we are going to first is step 1, if we want to say step 1, try to reduce the two particle system. Since this deal with 2, right? 2, 1 particle system. That makes the calculation or equation, number equation also reduce, right? So that is the first goal. How to reduce 2 particle to 1 particle? Okay, now think about we have let's say M1, M2. Let's just consider whatever the coordinates here. So we have R1. This is the origin here, right? So that's R1 position of particle 1, R2. Okay, now we are going to introduce a center of mass. Center of mass. So now first, we already discussed the center of mass in chapter 1, right? So I just immediately write down the formula. Since this M2 R2 divided by M1 plus M2, right? That's introduce the center of mass R. Okay, so if we introduce the center of mass, now I'm going to also the position of M1 respect to capital R. So now I'm going to use R1 prime, and then from the center of mass point to the M2 is R2 prime. Okay. So once we introduce this, so then we can find the relation between R1 prime, R1 and R, R2 prime, R2 and R, right? Okay, so therefore we have R1 prime equal to, because this is R, capital R plus R implies R. So R prime is R minus capital R, right? R1 minus capital R, right? Then you can substitute the capital R, you will see here, R1 minus M1 R1, M2 R2, M1 plus M2. Then you multiply M1 plus M2 numerator, and then you have so you have M1 plus M2 R1, then you can cancel that one. So finally you will have M2 R1 minus R2, M1 plus M2, right? And similarly, R2 prime is R2 minus R, and do the same thing, R2 minus M1 R1 plus M2 R2, M1 plus M2, then that equal to M1 R2 minus R1, M1 plus, you can double check yourself. Okay, so now we introduce relative position R. The R, okay, now if we say this R2 minus R, so that is R, we center from M1. Use green color. Let's use blue again. So here, I center here, I define, introduce R. Okay, that means now I select one of the particle as the center of origin. Then So that is R2 minus R1 I introduced. Then you can see R2 minus R1. Then, okay, so now here, R1 prime, R2 prime, oh, okay, you can use it. That's a group, right? So now, if I define R as R1 minus R2, or R2 minus R1, so R1 prime is equal to here, negative, right? You just switch, so that is negative M2R M1 plus M2. And R2 prime is plus M1R M1 plus M2, right? Here. Okay. So now, once we introduce this, let's keep in mind here. Okay. I think that's enough. Okay. So now, you can see if we want to calculate the system of these two particles, we can use either R1, R2 as variables, or center of mass capital R and the relative position R, right? So now we are going to choose center of mass R and R as our coordinates. To describe this, right? This system, right? Because the force, okay, Ig, the force is minus gradient of this potential, and we know that's negative of this gradient of potential along the R head, right? Since the force along the R, not R1 prime, not R2 prime, and not R1, not R2, is along the R. That's why we choose R, right? So this belongs to this. So we select this. Now let's write down the Lagrange. That is because it's right, we select this one. It's a good choice. So now the Lagrange is be the kinetic energy minus potential energy, right? The kinetic energy now we are going to write it in terms of the R, capital R, lower R, and the capital R dot, lower R dot, right? Since we select these two as general coordinates, and potential is only a function of lower R. Okay. I think that is, if in general you can also, I don't think that is in this case. In general you can include this, but later you will see it will not include it. Does not depend on these two, right? Only depend on R. So now, if we write this way, we are going to rewrite kinetic energy. That's first, kinetic energy is equal to half of M1 R1 dot square plus half of M2 R2 dot square, right? So now, as I mentioned in chapter 1, you can either write down the total kinetic energy in terms of each individual, or I classify into the center of mass kinetic energy and the relative kinetic energy. In this case, it is easier to use center of mass plus relative. I'm going to write this way. So that what this means, center of mass, the kinetic energy, we know that is half of M1 plus M2, right? Total mass, and R, capital R dot square, right? And the relative, so now relative we have two terms. One is the first particle R1 prime dot square, right? Relative means is this particle right to the center of mass, right? This is center of mass position. So that is R1 prime, R2 prime, not R1, R2. Plus, so this is a prime, plus second particle M2, R2 prime. Square. Okay, let me too many, so I'm going to use these parentheses. Square plus half of M2, R2, 1, square. Okay, now we are going to use this. Since now we choose capital R and lower R, this is a R1 plane, R2, so we are going to replace R1 plane in terms of R, right? So substituting to this, let me just first still keep this, okay. I think I just focus on this enough. So let's just focus. So this one, you will see is, let's see, T prime is here, right? So T prime is a half, let me write down again, R1 prime square plus half of M2, R2 prime. Sure. And then we substitute into that, that is half of M1. This R1 prime, so we do the dot, is only R dot, right? So that the M mass all are constant. Then we have minus M2, M1 plus M2 square, R dot square, right? And the second one is half M2. Then this is M1, M1 plus M2 square, R dot square. Then you can try to combine together. So now let me give you the final space here. Keep continue here equal to. We organize that because that's all R dot, so we have half still here, and M1 plus M2 in denominator, and numerator product M1, M2 R dot square. Okay, so we have a TCM, that is the center mass kinetic energy and relative kinetic energy. So now final, this Lagrangian is half of M1 plus M2 R dot square plus half of M1, M2, M1 plus M2 R dot square. What's it? Minus 3. Sorry. So now we define or introduce, we call the reduced mass mu, which is this term. So now L is, and the capital M is this total mass, right? So now we have a half of a capital mass, R dot square plus half of the reduced mass, lower R dot square minus 3. So you see the function is no capital R, right? Only the R, sorry, here R, and capital R dot, lower R dot, and maybe time. So what that means? Right? It is cyclic. That means Lagrange does not depend on the center of mass position. So what that means, the partial L, partial R dot equal to 0, right? Sorry, total. D, T, partial L, partial R dot is equal to 0, right? And that is means partial L, partial R dot. Sorry. If you remember, this is a center of mass. Linear momentum is this one, right? By definition, is the conjugate momentum over this correspond to R, right? That means that is equal to constant. And that is we analyzed before. Yes, those are consistent. So now, if that is case, we are going to write this way. So you see here, because this is constant, so this is also keep constant, right? Then the total Lagrange, actually the variable is this one. That means this motion, this two-particle relative motion as a system under the central mass. This the key to characterize the motion is here, right? So we are looking for the relative motion. So now we are going only to focus on L prime. Because only L prime can give us this in details which we are interested, right? Okay. So if this is L prime, then now let's rewrite L prime. What is L prime? We have a half of a reduced mass r dot square minus v, right? But now, because in the center force, v actually is function r only. So now we have L prime is, that is a general case, but I think now we just consider, I think actually it is also only absolute value of this r, right? Okay, now we can apply the Lagrange equation. Since now we are going to apply the Lagrange equation, suppose, so here this is only the variable, right? If you select this one, later we are going to do the data, so this x, y, z, right? 3 general coordinate, so that means partial d dt, partial xi, let's say xi dot, partial L xi equal to 0, so xi is either x or y or z. So the remaining part is we are going to solve this. Okay. And now we are going to do further analysis because as I will say that do not immediately go to deal with this mathematically, since again still here we need to do some analysis, try to see if we can extract the information that's useful and make this solve this problem become simple or easier. So here an analysis. Because we know, right? We know what? We know the, okay, first one, the center force, this one is proportional to the r, right? So that means only along the ri direction. And already obey the strong, right? And then second one, it has a spherical symmetry. Spherical. That means, okay, this the force actually is only the function of our magnitude. The magnitude. So the force, when the magnitude is the same, it will have the same value, and then change the r, then change another value, right? So that is spherical symmetry. That is we define the central force, spherical symmetry. Number 3. So the torque is equal to r cross product with this one, right? And since r and Fij is parallel, so this is equal to 0. And that we also analyze. Now the total torque is to 0. So the dl prime, since here we just consider prime enough, since this we focus on this only function r, right? So that is prime is also 0. So L prime is constant. Well, that means constant. Constant because the angular momentum is both vector and this vector, so we have a direction. And the magnitudes, they all are constant, right? That means constant. So that means, let's consider L is, right? Because, okay. Sorry. This L is angular momentum. This L is angular Lagrange. Sorry, so that's why I do not. Be careful, even though we use the same L. This is Lagrangian. This has a vector that is angular momentum, right? So now angular momentum, because you go to this one, right? So if this is a constant, okay, suppose we have this angular momentum in space here, and the orbital perpendicular to this angular momentum, right? Okay, so now here, if this is, that is r, right? And if p is here, right? Now, so this is a constant, and then if you just select the arbitrary coordinates, suppose this is z, and this is an x, this is y, right? So we have the angle between, okay, I think that's what it is. If this is n hat, right? Okay. So that means in this case, the if this constant, so r, p perpendicular to L, right? Both r and p perpendicular to L. Okay. If perpendicular to L, then we can select, that's just, so we can select the new coordinates, which is just because this, right? So select, let us select the x, y plane such that this plane, the L is perpendicular to the x, y plane, and then the R and the P is on the x, y plane. That is we select. Because it's L is constant, means direction will not change, right? It keep. If direction change, so all the motion of the R, P is always perpendicular to the R, to the L, that we know. Then why not we select the x, y plane as our coordinates to remove this x, y, z, just select z along, that means z parallel to L, right? If we select z parallel to L, then the x and y is on the plane which x, R and P. And R and P is what we interest. So now let's back to here. So this one I'm going to rewrite here. Okay. That is x, y, z parallel to L. So here any position R is here, right? And the momentum here. Then we are going to characterize the position of this angle. We are going to use polar coordinates, right? Since here, so that one either x, y, or r and theta. Polar. So usually we use polar coordinates since this one is better to characterize the motion, because here that's a good choice of the general coordinates since r is this is r, and also force is function r, and potential is function r, right? So that if you select x, y, it's always x squared plus y squared square root, right? That is make count. So now that is, you see here. Initially, we found these two general coordinates, capital R and lower r. Then after we analyze the capital R, the central mass does not change its momentum, so that is, we do not interested. We are interested in the relative motion. And in relative motion, the lower r in general is 3 general coordinates. But when we analyze, since we have one condition, angular momentum constant, so that reduced to only 2 general coordinates, right? So okay, now let's write down this Lagrange equation. First, Lagrange. Lagrange is the P prime. Okay, let's still use prime and V. Now, from now on, we just replace L, Lagrange, the prime, remove the prime. So we focus on the relative. It's T minus L. So T also remove prime. And then here, T is half of reduced mass, right? Half reduced mass, and okay, even here we also replace by the particle. So you just know that this mass be the reduced mass, so that just make this simple or general, right? So now, then r dot square plus r square theta dot square, right? That is the polar coordinates, the kinetic energy is square, and potential energy is function r. So you can see here that is a function of, we have r, we do not have theta. We have r dot and theta dot, and also does not depend on time explicitly. What's something new come from here? So as we said before, we do the details, we need to find which, during, in this Lagrangian, is there any cyclic coordinates? See that, right? That is, again, so what this means, there must be another quantity which is conserved according to the conservation theorem that corresponds to this cyclic. We have conjugate momentum, or we call it kinetic momentum, which is being constant. Because, right? So P theta equal to partial L partial theta dot is, okay, L is here, right? Partial L partial theta dot, we have a factor 2 cancels, that is m r squared theta dot. That's equal to constant. Now we give a name, or give an index L, because this corresponds to the angular momentum, right? So this is the angular momentum. Why it is an angular momentum? Since this is the angle, the general coordinate is angle, and we know associated with the general coordinate is angle, they associate with the conjugate momentum is angular momentum. Conserved. So that is the first, we call this, you see here, this equation reduced from this, if you go to the Lagrange equation, that is the second order derivative of this theta, but now it's the first order. So that is the first integral, is also called the first integral from this problem. First integral, and later we'll have a second integral. So you see here, immediately we solve, we do not need to go to the details, go to the second order differential equation of Lagrange equation, we just immediately got this one from this cyclic. So, now before we go, okay, so here, let me, since we introduced L, now we need, from that equation, if I'm going to say this is a very important equation, equation 1, and from the equation 1, we can add theta dot, okay? From there, theta dot is L m r squared, right? So what that means, we want to solve the Lagrange equation to try to find the theta as a function time and r as a function time. That is the equation of motion for the hyperbolic trajectory. Now we have it. That is the theta dt, right? So if you do the integral, okay, let me do this one. The theta dt. So now I'm going to. Okay, so can you see that is L m r squared t. So if so, theta is the function of do this one, right? If it okay, theta, there's a theta t and theta naught, right? this one is equal from T naught to T. You do that, so this is T naught to T. Then the left-hand side is equal to plus T naught to T L M R squared dt. Looks like very easily we can get this solution. The question is yes or no. Here. R is function T, we do not know. So later you will see this integral is not easy because R. But let's see, so that is why, let's say equation 2, that gave us the first integral immediately. You see, I didn't apply the Lagrange equation, right? I just analyzed. So I immediately got this equation for theta. Now before we do the R, let's because from here by product we have another physical quantity is a constant, so that's interesting, and that is k plus a second log. So now let's introduce this one. Okay. Let's do this. Suppose this is orbit, right? So the orbit and a time t is here, and then at time delta t equal to here. So now we have this r, if this d theta is very small. Okay, so that is r. Then this area, we call this area is, if this is very small, so this is pretty much represented by this one, we call the sweeping area. So this sweeping means the particle move along this orbit, sweep, and sweep, so this is a dA. This is pretty much like triangle, right? So the half of r, and multiply this is r d theta, right? So that is half of r squared d theta. This is a sweeping area. Okay, so now look at this one. How about this one? Now let's from p theta is constant, right? Okay, just say. dp theta dt is equal to 0. Then now dp theta d dt. P theta is p here. This one, right? mr squared theta dot. mr squared theta dot. So that's be equal to 0, and now this is constant, so that means d dt, I'm going to multiply constant r squared theta dot. That's also equal to 0. Do you agree? Since here d mr squared theta dot equal to 0, then the m is constant, so that means dr squared theta dot is 0. Then I multiply half. So half of r squared theta is also 0, right? And that is what? What did I? Okay, yes. Yes. So here, in this case, the dA dt, if dA is this one, dt is r, sorry. Half r squared theta dot, right? If dA is, then I divided by dt is this, so that is this one. That means dA dt is 0, so A is constant. This is another byproduct. Give another conservation quantity. This quantity is what Kepler observed. In fact, whenever the particle sweep, so for example, sweep here, if at the same time, but the area, you see here, so we always keep safe. So if this is and theta now, dA1 is a dA2. So if, okay, because if dt the same, right, dt1 equal to dt2, then we have that is Kepler's second law. That means, look at this planet, for example, move around the sun, or the Earth move around the Earth. The Moon move around the Earth, and you can see. Let's count that, for example, 1 minute, and see how much they split the area. And second, next 1 minute, this will always equal to 0. That is come from this analysis. So that is the product. Okay. All right, let me stop here. I think we need time give you the final the midterm exam, and so you can start work on this. Can you deliver this to the others? You forgot. You want to answer the questions for them?
Answer all 4 of us.
Yeah. Okay, so just quickly read, and if you have any question. We have totally also 5 problems, and this, as I said, the chapter 1 and 2. So the first one, I give you this formula for this non-holonomic constraint formula in general, and then just ask you proof if they satisfy the semi-holonomic constraint, the condition. That means in class we prove that this one, right? You prove this, but I want you to prove that it means this 2 conditions also satisfied. Okay. And of course here f is f alpha is function of is this holonomic, so only function of general coordinates, not general velocity. Second one is consider is in the electron field, we have potential phi and the vector potential A. Then if we change or use the gauge transformation A to A plus some the delta, the gradient of phi and the potential, to another term. So look this, the Lagrangian and Lagrange equation will still keep the same amount. That's proof. Number 3 is this Artwork machine. We discussed in the class. Without consider that the Pauli mass is 0, massless. Now it is not 0, so it's have rotation. Now when I say the fractionless, it just say this bear is a fractionless, right? I think it's now you understand the meaning. Okay, so that means you need to consider rotation of the Pauli. And so this and see this. The constraint, what kind of constraint, and also find this the force, general force QG as function, associated with each different constraint. Number 4 is another case. If you the particle move in the loop and only consider the gravitational potential, so just solve this one and discuss some critical angle theta naught. Last one is the concept of the energy function which we discussed today. So give you the system and try to write down this Lagrangian energy and energy function and check whether they are conserved or not, whether h equal to E, depend on different choice. There are 2 coordinate values in the line. You can select x and y. Another is relative to rotation system, so you can select another. Did I give you the suggestion? R and L, right? So then you just discuss in this case and derive this energy function in each case. All right, not so complicated, yes.
Like 2 small questions, like in the third one, like do we have to consider the kinetic energy of the Pauli also, the rotational kinetic energy?
You mean which one, problem 3 or 4?
I have two like questions like problem 3, the pulley when it rotates.
Yeah. You have the kinetic energy, which kinetic energy?
Of the pulley.
Pulley fixed, just rotation.
Oh, so rotational.
Just rotation, yes.
Okay, and in 2 we have to like ignore the effect due to gravitational.
Yeah, but even in that case, we just consider this tool, right?
Not that one.
No?
I mean, that is okay. Like in the second question, the charge.
Yes, number 4, second question.
Charge particle.
Charge particle, yeah. You have kinetic energy, yes?
Yeah, there we ignore the gravitational like effects.
Yes, yeah. Gravitational, yeah, relative, yeah. Gravitational, yeah, you ignore the gravitational, just electric field and magnetic field, yes. Okay.
Thank
Well,
you.
do yourself and independently and show me. If you have any questions, do not understand what the question, let me know. Either email me or stop my office. So for you both, I'm going to grade and put it into your box.